Welcome to our series on essential concepts and terminology in transportation planning. In this lecture, we will explore the fundamental concept of the trip distribution.
Trip distribution is the second stage of the traditional four-step travel demand modeling process. In the first stage, trip generation estimated how many trips are produced in each traffic zone and how many trips are attracted for activities. In the second step, trip distribution, these results are used to estimate how trips actually move from one zone to another. Specifically, the core task of trip distribution is to construct a production attraction or PA trip matrix, which represents trips moving from trip producing zones to trip attracting zones, segmented by trip purpose. This matrix serves as the fundamental input for the subsequent modal split analysis. Furthermore, these data are eventually converted into an origin-destination matrix for use in analyses that require specific directional flow, such as traffic assignment. The analysis process, like other forecasting models, is divided into a model calibration stage and a forecasting stage. In the model calibration stage, an appropriate predictive model is developed by identifying the underlying spatial interaction patterns based on observed data, such as household travel surveys. In the subsequent forecasting stage, future trip productions and trip attractions are input into the calibrated model to estimate the final PA trip matrix for the target year.
There are four generally recognized models for calibrating and forecasting trip distribution: the growth factor model, the gravity model, the entropy model, and the intervening opportunities model. In practice, the growth factor model and gravity model are most commonly used. Since the entropy and intervening opportunities models are less frequently utilized in professional applications, we will focus our discussion on the growth factor model and the gravity model. While the theoretical origins of these formulation-based models, such as the gravity, entropy, and intervening opportunities models, differ, they share a common mathematical basis. They are all derived based on the choice probabilities of travelers. Notably, these three formulation models share mathematical lineages with the logit model used in mode choice analysis, meaning they operate within a similar framework of theoretical interpretation. Given these conceptual connections, the gravity model has emerged as the standard practice in the field of transportation planning. Its prominence in professional application is due to its relative computational simplicity and its superior efficiency in analyzing aggregate travel patterns compared to more complex formulations. In addition to these aggregate models, research continues into applying discrete choice theory to understand individual travel behavior at a disaggregate level. However, in real-world planning, networks often contain hundreds or even thousands of traffic analysis zones, creating a massive pool of destination alternatives. Because these individual-level models require immense computational power and highly detailed disaggregate data, they have remained primarily within academic research. Consequently, the simpler aggregate gravity model remains the preferred tool for practical applications. Growth factor models estimate future interzonal travel demand by scaling base year trip volumes using a specific growth factor. Here, the growth factor is expressed as a function of base year and predicted future trip volumes, and the basic zonal growth factor is defined as the ratio of predicted future trip ends to base year trip ends for each zone. These growth factors can take the form of a single system-wide average growth factor applied uniformly to the entire PA matrix, or zone-specific growth factors calculated based on forecasted trip productions or attractions. Because these models rely solely on observed base year and future target trip data without requiring complex external variables, they do not necessitate a separate model calibration process. Consequently, growth factor models can be applied in a relatively simple and straightforward manner. They are generally classified into three types. First, the uniform growth factor method is the simplest form. This approach derives a single system-wide average growth factor and applies it uniformly to all production attraction zone pairs. While the computational procedure is very simple, this method cannot reflect differences in growth patterns across individual zones. Additionally, the resulting trip totals do not match the trip production and attraction forecasts obtained from the trip generation model. Second, the singly constrained growth factor method scales future trips based on the zonal growth factors of either the trip production zones or the trip attraction zones, but not both. Under this method, the trip totals on the constrained side will perfectly match the trip generation forecasts, whereas the totals on the unconstrained side will not. Third, the doubly constrained growth factor method is the most sophisticated approach. It mathematically combines the zonal growth factors of both production and attraction zones simultaneously to ensure that the final PA matrix satisfies the target forecasts on both sides. Typically, a single calculation cannot satisfy both constraints at once. Therefore, the model requires an iterative adjustment process until the estimated trips converge within an acceptable error margin. This iterative process has only computational meaning in aligning both production and attraction volumes to their respective targets simultaneously, and has no behavioral meaning regarding how actual travel behavior evolves. It simply assumes that the base year travel pattern remains unchanged in the future and mathematically adjusts the flows to match the forecasted totals. In practice, this doubly constrained model is the most widely utilized growth factor method. The most representative methods for doubly constrained growth factor modeling include the average growth factor method, the Detroit method, and the Frater method. While these models share the same fundamental objective of ensuring that the final matrix matches both production and attraction forecasts, they differ in their mathematical efficiency, specifically in how quickly and accurately they converge to those target values. All growth factor models share a consistent core concept. Future trips are estimated by multiplying base year trips by an appropriate growth factor. The doubly constrained methods follow this exact same principle, differing only in the mathematical formulation used to calculate the composite growth factor applied to each matrix cell. The key distinction is that due to the dual constraints, these models cannot achieve the targets in a single step and require an iterative process to reach convergence. Although the specific composite growth factor formulas for the three methods shown on the screen differ from one another, the principle of converging to match trip production and trip attraction forecasts through iterative calculations is the same. The shared algorithmic framework for doubly constrained growth factor models follows a five-step iterative process as shown on the screen. In Step 1, initial zonal growth factors for each traffic zone are calculated using the observed base year trips and the forecasted future target trips. In Step 2, these calculated zonal growth factors are input into the respective model formulas to determine the composite growth factor for each individual zone pair. In Step 3, the base year trip volumes are multiplied by these calculated composite growth factors to obtain the preliminary future trip volumes denoted as PAIJ n+1. In Step 4, these calculated zone pair trips are aggregated by row and column to compute the estimated total production PI and attraction AJ, which are then compared against the forecasted future target values. Finally, in Step 5, if the maximum discrepancy across all zones falls within the acceptable error margin epsilon, the calculation is terminated. However, if the errors exceeded the threshold, the newly estimated trip volumes PAIJ n+1 overwrite the previous values as the updated baseline data PAIJ n, and the procedure returns to Step 1, repeating the cycle until full convergence is achieved. Among these models, the Frater model is renowned for converging to the dual constraints most rapidly with the fewest iterations. Due to this computational efficiency, the Frater model is the most widely used in tactical transportation planning. In addition to future forecasting, the Frater model is also commonly applied in the trip matrix expansion process, where sample survey data is scaled up to represent the entire population. As its name suggests, the gravity model is an application of Newton's law of universal gravitation to the transportation field. Just as gravity between two objects is proportional to their masses and inversely proportional to the distance between them, the gravity model is based on the principle that the trip volume between two zones is proportional to their respective productions and attractions and inversely proportional to the travel impedance, such as travel time, distance, or generalized cost. Formula shown on the screen represents the production-constrained gravity model, which is the most widely used version in practice. This formula determines how the total trips produced at a specific zone are distributed among various attracting zones. The denominator represents the sum of attractiveness across all potential attracting zones, while the numerator represents the attractiveness of one specific attracting zone. Essentially, it is a probabilistic model that distributes trips based on an attracting zone's share of the total aggregate attractiveness. This proportional structure is then multiplied by a friction factor, which quantifies travel impedance and captures the empirical tendency for trip likelihood to decrease as travel distance, time, or cost increases. The friction factor may vary across regions and over time, depending on prevailing conditions. Differences in land use patterns, income levels, vehicle ownership rates, and other socioeconomic characteristics can influence how travelers perceive and respond to travel distance or time in different areas and periods. For this reason, before forecasting future trip distribution patterns, it is necessary to analyze observed travel behavior in the base year to identify how travelers respond to impedance such as distance and time. This process is known as the calibration stage of the gravity model. By accurately estimating friction factors that can closely reproduce observed trip length distribution, or TLD, patterns, the gravity model can produce forecasts that are both accurate and reliable. In practical applications, the most widely used calibration technique is the tri-proportional approach. The purpose of this method is to align the model-estimated trip distribution with the observed travel patterns across different trip length intervals as closely as possible. The calibration process using the tri-proportional approach proceeds as follows. Step 1 is the initialization stage. In this stage, all initial values of the friction factors are set to 1. Simultaneously, based on observed data, a trip distribution by distance interval is constructed to establish the target trip length distribution, which serves as the final convergence criterion the model must achieve. Step 2 is the trip distribution allocation stage. Using the currently specified friction factors, the gravity model equation is applied to compute the PA trip flows between all pairs of traffic analysis zones. Step 3 is the trip balancing stage. In this stage, the estimated PA trip flows are balanced so that the calculated totals match the target trip production and attraction forecasts for each zone. This is achieved through an iterative zonal balancing procedure, which can be implemented by applying either the furnace or the Freitar method, depending on the practitioner's choice. Step 4 is the error checking and iterative calculation stage. Based on the balanced trip volumes, the model's trip length distribution is derived and then compared with observed values. If the discrepancy between the two distributions falls within an acceptable error range, the calibration process is terminated. If the discrepancy is larger than the allowable error range, the friction factors are adjusted using the ratio of observed to estimated values, and the procedure returns to step 2 for further iteration. Through repeated adjustments, the model's predicted trip patterns are gradually brought into alignment with the observed trip length distribution patterns. Through this systematic calibration process, a forecasting model can be developed that reflects the spatial trip distribution characteristics of the study area. In gravity models, instead of estimating friction factors separately for every distance interval, travel impedance is often represented using a single mathematical formulation, commonly referred to as an impedance function. The basic gravity model primarily accounts for attractiveness and travel impedance while omitting other socioeconomic variables. Therefore, when using actual data, outliers in the calibrated friction factor values may occur in specific distance ranges due to other unaccounted factors and insufficient sample sizes. However, applying an impedance function helps smooth out such anomalies. This ensures logical consistency in travel behavior by satisfying the fundamental assumption of the gravity model that travel impedance increases with distance across all distance intervals. For this reason, impedance functions are often incorporated into gravity models to maintain behavioral and logical coherence. Despite the term impedance function, its role within the gravity model formulation may appear conceptually opposite to what the name suggests. Specifically, within the gravity model formulation, a larger impedance function value leads to a greater volume of trips distributed to an activity destination. Therefore, when interpreted as the inverse of travel impedance, the impedance function is more accurately interpreted as representing the strength of travel attraction as a decreasing function of distance. The impedance function is a function that has a similar shape to a trip length distribution curve, which depicts trip frequency by travel distance. There are three commonly used forms of impedance functions. One is the negative power function, which takes very large values near the origin and decreases sharply as distance increases. This form reflects strong attraction for nearby destinations and rapidly diminishing attraction with distance. Another commonly used form is the exponential function. While it shows a curve shape similar to the negative power function, it differs in that it approaches a finite value at zero distance rather than infinity. This implies the assumption that basic impedance exists even for very short distances. Then there is the modified gamma function. Depending on its parameter values, different function curves can be expressed. Notably, this function form can describe a pattern where travel attraction is maximized not immediately near the origin, but rather at a slightly distant point, after which the attraction decreases as distance increases. This function is suitable for explaining travel patterns where travelers prefer activity destinations at moderate distances rather than extremely close locations. To apply an impedance function within a gravity model, the parameters that define the shape of the function must be estimated. In practice, the friction factors by distance interval derived through the previously described tri-proportional approach are used as input data. Statistical techniques, such as linear regression analysis, are then applied to determine the impedance function form that best reflects the travel characteristics of the area and to estimate its coefficient values. A well-calibrated and generalized impedance function enables the gravity model to produce stable and logically consistent predictions of distance-based trip distributions in accordance with the model's fundamental assumptions.
The forecasting phase of the gravity model is theoretically straightforward. It involves inputting the future trip productions and attractions by zone into the calibrated gravity model formulation. In practice, the most commonly used form is the production-constrained gravity model. By its structural design, the estimated trip productions exactly match the forecast totals, whereas the estimated trip attractions generally do not. Therefore, to maintain logical consistency in transportation planning, an additional balancing process is required to ensure that both production and attraction estimates satisfy the doubly constrained conditions. To achieve this zonal balance, practitioners typically employ either the furnace method or the Fertar method. As illustrated on the screen, the furnace method resolves this discrepancy through an intuitive row and column factoring process. It first adjusts each column by multiplying the values by the ratio of forecast to estimated attractions, a step known as column factoring. Since this alters the row totals, the next step applies the corresponding ratio of forecast to estimated productions to each row, known as row factoring. By alternating sequentially between row and column factoring, the matrix gradually converges until both totals match the forecast values within an acceptable tolerance. Alternatively, the Fertar method can be applied here as well. While the Fertar method utilizes a more complex mathematical formulation based on relative accessibility and growth factors, both methods successfully guide the matrix to full spatial convergence.
Notably, these balancing techniques are utilized not only in the forecasting phase, but also during the calibration process of the trip proportional approach. By simultaneously converging the three fundamental components, trip productions, trip attractions, and friction factors, they enable a consistent and reliable forecasting process that properly reflects the trip length distribution patterns of the study area. Gravity model fundamentally assumes the destination choice is influenced by two primary factors, attractiveness and travel impedance, such as travel distance or time. However, in reality, various other elements, such as socioeconomic elements and regional characteristics, also influence travel behavior. To indirectly account for these additional influences, a zone-to-zone adjustment factor, known as the K factor, is sometimes introduced into the gravity model. The K factor serves to bridge the gap between the gravity model's estimates and observed values. It is possible to assign fixed constants to specific zone pairs to achieve a perfect match with current observations. However, this only matches current conditions and prevents the model from flexibly reflecting future environmental changes. In other words, this approach improves the model's explanatory power for existing conditions, but it does not improve its predictive capability under changing circumstances. Therefore, K-factors are generally used restrictively, such as in major city centers, where powerful socioeconomic influences overwhelm distance resistance, where geographical barriers like rivers or mountains create psychological resistance far exceeding physical distance, or where strong commuting ties exist between specific employment hubs and residential areas. It is essential to recognize that K-factors are a supplementary tool. Applying them only to areas with distinct, long-term regional characteristics ensures a more reliable forecast. While the standard gravity model is designed for typical interzonal movements, specialized categories like external and intrazonal trips require unique modeling strategies, as their travel impedance cannot be easily defined under standard formulations. For external trips entering or leaving the study area, future demand is typically forecast by extrapolating historical trends or by applying growth factor models. This is because friction factors for external regions cannot be estimated in the same manner as for internal networks. For intrazonal trips, movements occurring entirely within a single traffic analysis zone, a common practice is to allocate a certain percentage of the zone's total production as internal travel. If these trips are to be analyzed within the gravity model framework, a hypothetical impedance value may be introduced using assumptions based on zone radius or distances to adjacent zones that reflect local conditions. Rapid advances in mobile and data technologies are bringing about a fundamental transformation in traditional trip distribution analysis. Historically, trip distribution has relied on sample-based data obtained through household travel surveys, which require substantial time and financial resources to conduct. Moreover, because survey-based data depend on respondents' memory and self-reporting, they have inherent structural limitations, including omitted activities and unintended distortions of travel and activity information. In contrast, modern mobile technology enables the passive and automated collection of location-based data in real time. Mobile big data, derived from cellular network signals or GPS, records actual human movement patterns with highly detailed spatio-temporal granularity. This means that by simply aggregating massive volumes of individual trip records, it is now possible to construct near population-level PA and OD matrices without the complex expansion procedures that were previously required. Furthermore, data fusion, which combines different data sources, makes it possible to establish a more comprehensive and reliable information system. By combining mobile location data, navigation route data, public transit smart card records, and license plate recognition system data, the inherent gaps and weaknesses of individual datasets can be mutually complemented. For example, Combining individual movement trajectories from mobile phone data with public transit usage information from smart card records results in a more complete data set that captures both precise movement paths and specific mode choices. Such data fusion enables the accurate and cost-effective development of time series PA and OD matrices. While institutional barriers regarding privacy protection exist, technical solutions that allow public benefits and individual privacy to coexist are steadily evolving. As these institutional and technological challenges are resolved, fused big data is expected to become the most trusted standard foundational dataset for transportation analysis in the near future, providing the transportation field with richer and more comprehensive information than ever before. In the next lecture of our series on essential concepts and terminology in transportation planning, we will focus on the topic of the mode choice. Thank you for watching. I would love to hear your thoughts or comments on today's lecture. If this explanation was helpful, please like and subscribe to support this series.